Hey guys, Adam here with another technical video. In this video we shall investigate the common myth that heavy aircraft dive better than light aircraft to see if it holds up to scrutiny. I'll also provide examples of dives and why enemies sometimes catch you even though your aircraft supposedly dives better. As always, my models are based on the War Thunder flight model data files. Without further ado, let's MCAS right into it. First off, we need to define the terms we'll be using in this video. What do people mean when they say that a certain aircraft dives well? Who knows? They could mean that it has a high rip speed, that it accelerates well in a dive, or even that it has good high-speed handling. Except in some Russian and Japanese aircraft, the rip speed is usually not a relevant factor in dive performance. Instead, in this video I'll be evaluating the dive acceleration of different aircraft at different speeds to compare their dive performance. To adequately compare something like dive acceleration, we need to program the aircraft models and numerically simulate the dive. Simulation is a very powerful tool, but it's only as accurate as your model. So, before going further and starting to compare dive performance, we must make sure that the models are accurate. To do that, I'll go into test flight and dive and compare side by side the simulation and the test flight to make sure the simulation is valid. The two aircraft models I built are the P47 D25 and the A6M5. Both are at 4.3 BR. This is the ideal matchup because the P47 is one of the heaviest single-engine props, while the Zero is one of the lightest single-engine props. This matchup will allow us to evaluate if heavier aircraft truly dive better than lighter aircraft, which is a common thing to hear from US pilots complaining that they were caught in a dive by Japanese aircraft. Let's test dive the P47 D25. I'll aim to start the dive at around 2,500 meters, so the plan is to go vertical as I pass 2,000 meters to bleed speed and start the dive at low speed and in a near 90-degree dive. It's not that easy to perform a nice dive due to the camera, but I did my best. The test data is logged using Void May. And that concludes the test dive for the P47. The same dive test was done for the A6M5. Now let's compare the test data to the simulation to make sure the simulation and models are accurate. On the altitude as a function of time graph for the P47, you can see that the simulation curve in blue and the test curve in red are essentially identical, which is great news for the simulation accuracy. The speed as a function of time graph on the right also shows nearly identical results for the P47, which means that the simulation is accurate. The same can be said for the A6M5 model as we compare the simulation to the test data. The kinks in the test curve are due to freezes and the wing rip near 700 km per hour. All in all, the simulations are a good representation of reality in War Thunder. Now that we have verified the models, we are ready to tackle the topic of this video and compare aircraft dive performance. As stated previously, we will be comparing dive acceleration at different speeds to see which aircraft dives better. First off, to directly see if heavier aircraft truly dive better than lighter aircraft, we need to keep drag and power equal and only change weight. To do that, we'll compare the dive performance of a minimum fuel P47 and a maximum fuel P47. The maximum fuel P47 is 700 kilograms or 12% heavier than the minimum fuel P47. Let's simulate the dive and graph their respective accelerations as a function of speed. The acceleration as a function of speed graph shows how quickly the aircraft are accelerating in a 90-degree dive. The aircraft with a higher acceleration has the advantage in a dive. This graph contains a lot of information if you know where to look, so let's go through it. The curves start at 290 km per hour TS, which is around climb speed at 2,500 meters. You can see that the minimum fuel P47 in blue accelerates better at low speed. That's logical, since gravity is accelerating both of them equally at 9.8 meters per second squared, and then the 12% higher power-to-weight ratio of the minimum fuel P47 makes it accelerate faster at low speed, which was expected. Already we can see that the myth of heavier aircraft diving better than lighter aircraft is not always true. As speed increases, however, the acceleration advantage of the lighter P47 reduces, until both aircraft accelerate equally well at 590 km per hour, with an acceleration of 9.8 meters per second squared at this speed. Coincidence? Of course not. 9.8 meters per second squared is the gravitational acceleration, and since both aircraft have the same thrust and drag, thrust equals drag when the aircraft is only accelerating with gravity. Another special note about when thrust equals drag is when the aircraft reaches its top speed, and 590 km per hour is indeed very close to the top speed of the P47 D25 at around 1 km of altitude. This is further proof that the simulation is accurate. Moving on, past the point at which the top speed at that altitude occurs, the heavier P47 starts getting the acceleration advantage, because the extra weight helps it keep a higher acceleration, since the same drag has a lower effect on a heavier plane compared to a lighter plane, and that advantage grows with the speed. So, just with this graph, we can conclude that the more weight hinders the dive until reaching the aircraft's top speed in level flight, and then helps the dive beyond that speed. Next up is a more interesting comparison between the P47 D25 and the A6M5, both on minimum fuel. Again, it's the same type of graph, with the P47 in blue and the 0 in red. We can finally evaluate which aircraft dives better. At low speed, in the beginning of the dive, the 0 has the acceleration advantage thanks to its higher power-to-mass ratio of 305 watts per kilogram, which also explains its better climb, compared to the P47's 231 watts per kilogram. The P47 starts getting the advantage at 400 km per hour thanks to its higher top speed. The 0 reaches its level of flight top speed first at 505 km per hour, while the P47 continues accelerating at a higher rate than gravity until reaching its level of flight top speed of 590 km per hour. The acceleration difference between the P47 and the 0 widens as the speed increases, and that's due to the lower drag to mass ratio of the P47 compared to the 0. As you can see on this graph, the P47 and the 0 have similar equivalent flat plate drag area, but the P47 has over twice the 0's mass, so it has a lower drag to mass ratio than the 0. The equivalent flat plate drag area of an aircraft is just how big of a surface is needed to produce as much drag as the aircraft itself when at the same speed. Interestingly, the equivalent flat plate drag area of 0.45 square meters is similar to that of a standing humans. So you'd experience approximately as much drag as a World War II fighter aircraft if you were upright and moving at the same speed. Pretty cool. If we look at the altitude as a function of time graph, however, the P47 only beats the 0 by 0.2 seconds in a 15-second to 1,500 meter dive. Why is the time difference so low despite the P47 having the acceleration advantage for most of the dive? That's because it takes time for an acceleration advantage to transform into a speed advantage, and then it takes time for the speed advantage to translate into a distance separation. And 15 seconds is not nearly long enough for the P47 to really pull away from the 0. To see the effect of increased time, and since most dives aren't 100% vertical, we'll simulate a 45-degree dive next. Keep an eye on the cute 737 MAX image on the top left, which shows the dive angle for the graphs that are being shown. Alright, next up is the 45-degree dive. Let's check out that graph. Again, the same tendencies appear, with the 0 having the low speed advantage while the P47 has the medium and high speed advantages. On the altitude as a function of speed graph, the P47 now finishes the dive 0.5 seconds before the 0 in a 22-second dive, which is a significant improvement for the P47 compared to the 90-degree dive. Next up is the 30-degree dive. Again, the same tendencies appear. On the altitude as a function of speed graph, the P47 now finishes the dive 1 second before the 0 in a 30-second dive, which translates to around 250 meters of separation at their speeds. The longer the dive, the better it is for the faster aircraft. Next up is the 0-degree dive, otherwise known as level flight acceleration, this time at sea level though. Again, the same tendencies appear. Indeed, not much is different between going in a straight line and diving. The only difference is that your aircraft has a bit less drag since it doesn't have to create as much lift-induced drag, and you reach higher speeds in a smaller amount of time thanks to gravity helping you. The simulation ran for 200 seconds, and the A6M5 reached its top speed of 490 km per hour, and the P47 almost reached its top speed of 565 km per hour at sea level. On the graph on the right, you can see the distance both aircraft covered in that 200-second simulation. It takes the P47 2 minutes to get 1 kilometer separation from the 0, again highlighting the lengthy process of getting separation from an aircraft when starting at equal energy states. Next up is me listing all the reasons why your better diving aircraft gets caught by worse diving aircraft in a dive. First off, the reason you're diving is because an enemy has a speed and or altitude advantage over you and you want to escape. If the enemy already starts at a higher energy state, it's going to take even longer to equalize energies, and he'll be closing the distance until you do. Second, in a typical dive, you want to dive at nearly 90 degrees to pick up speed quickly to enter the speed region where you have a high acceleration difference, and then pull up to maybe 20 to 30 degrees to increase the time you stay above your top speed and bleed the enemy's energy. When you pull up, the enemy can cut across and use a more direct route to you, and it'll look like he's gaining on you even if you're both going at the same speed. Third, dodging such as rolling and pitching creates extra drag and slows you down and helps the enemy catch you. What's more is that when you're pitching, for example when doing the dolphin dodge, not only are you creating extra drag, but you're also going in a wiggly trajectory, so an enemy going as fast as you will gain on you since they are going in a straight line. Next up are two clips. The first clip is to really show what equal speed looks like. I'm in the Tempest Mark II, which is one of the best diving props in the game. I dive a bit early against this RE2005, and you can see that the distance ticker stays constant, indicating that we're going at the same speed. The RE2005 still has a 1 km energy advantage, but he correctly predicts that he won't be able to catch a Tempest Mark II in a dive in this situation, and he breaks off. That's what equal speed looks like. If the enemy is gaining on you when you start the dive and he has an altitude advantage, it's very likely that he will catch you unless your aircraft is significantly faster than his. Next up is the second clip. This is a rare occurrence of me misjudging or writing off the energy state of an enemy, the BF-199 F4 trop in this case. It's fortunate that this happened recently, or I wouldn't have an example like this to show. You can see that he has a significant speed advantage over me, but I'm still looking at the Focke-Wulf 190 until I realize that the BF-199 will get into shooting range very soon, so I immediately stop turning and go into a dive. It's an F4 trop with gun pods, so I have a big speed advantage over him. He still gets to within 500 meters and desperately shoots as I start pulling away from him. However, the dolphin dodge can be beat, and I dodge until I'm no longer within shooting range. It was a close call. If I dove a couple seconds later, I would have likely gotten hit. Alright, time to conclude the video. So, to answer the title of this video, heavier planes do not dive better than lighter planes. That statement is too general to be true, and it's easy to find counterexamples such as bombers. A much more accurate assessment of dive performance is to say that the aircraft with higher power to mass ratio or climb rate will accelerate better at low speed, while the aircraft with a higher top speed will accelerate better at medium to high speeds. More weight only helps a bit when you're going beyond your top speed, and that doesn't happen often. Thanks for watching, subscribe for more, and I'll see you in your dreams. Stay useful.